Alright everyone, today we're talking about lesson 3, energy changes in a reaction. So we're going to move on towards the last lesson of chemical reactions, and we're going to discuss how energy itself changes as a reaction progresses. So the big idea today is all chemical reactions occur due to energy change. The universe wants to be in a lower energy state usually, and pretty much always. So, before we get started, we gotta get asked this question is, what is energy? Alright, so energy first of all is everywhere. You see this energy in many different forms, such as, for example, you see it in the form of light, you see it in the form of heat, you see it in the form of motion, and there's many other types of energy. It's the driving force that makes things move and stops, so it's a driving force. For motion. And you've learned a bit about energy already based on how molecules itself move. So you might remember rotational, vibrational, and translational previously. What you also got to know is that molecules are held by chemical bonds. And it's this energy that's going to help break or form these chemical bonds in a reaction. So, you're going in a reaction, bonds break and forms due to energy. So we're going to talk about this in two different ways: how bonds break and how bonds form, and what happens to the energy that occurs. So we're going to start off with talking about how do we break bonds. So let's discuss it right now in terms of an example. So let's say, for example, you have some water. So here's our example. Let's say that you have some water and you add energy to this water. What will happen? Well, you might remember decomposition reactions. When water is subjected to energy, it will decompose into hydrogen gas and oxygen gas. Now, of course, if you balance this reaction, you're going to see that this is what's going to happen. You're going to have two water molecules break apart into two hydrogen gas molecules and one oxygen gas molecule. So we need to add energy. We need to add energy in order for this to occur. So what happens here is that when you add energy, it leads to bonds breaking. You could think of this like a rubber band. When you add energy by stretching that rubber band, you're going to break it. And that's what's happening here. You can think of these bonds as rubber bands. But now let's talk about in terms of reactants and products. Which of them has more energy? The two water molecules, does that have more energy? Or does the two hydrogen gas molecules and the one oxygen gas molecule have more energy? Which side, the reactant side or the product side, has more energy? Well, if you added energy into the water molecule, then that means these two products should have more energy. And what ends up happening is you get a graph that looks like this. So when you add energy means that products have more energy than the reactants. Now, where are these energies stored? What happened to this energy? Well, the energy is now stored in, well, first of all, where did the energy go? It went to breaking bonds, but the energy you added now went to forming additional new bonds. So some of the energy might have went into forming this H2 bond. Some of this energy maybe went into forming this O2 bond. But this is the graph that shows this. Now, this reaction doesn't tell you how fast it occurs, just that it occurs in this direction. So let's talk about the opposite. How do we form bonds? Well, we form bonds because what happens is that when two atoms collides, they need to release energy to form a molecule. Because if they have too much energy, you could think of it as two basketballs. If they have too much energy and they collide, they're going to not stick together. So they'll bounce apart because they have too much energy. Likewise, to break bonds, you need to absorb energy. To break bonds, it means to absorb energy. While to form bonds, you need to release energy. So, if we write an example for this one, what it will look like is this. Let's talk about backwards for the water example. So you're going to have hydrogen gas, and it's going to react with oxygen gas. And when that occurs, you're going to form water molecule, but you're also going to release some energy. So again, we keep it balanced. So this time you're going to release energy. And because you release energy in this situation, what ends up happening is that your products will now have less energy. So the products will have less energy than the reactants. And if I show this to you two different ways, you can see why. So in this case, you need to release some energy for these two to react to form the water. So that's where you see it in the equation. You need to release energy for this to occur. That's why this water actually has less energy than these two reactants. You could also think of it as an equal sign. If this arrow is an equal sign, in algebra, you gotta make sure your left-hand side must equal the right-hand side. So if the left-hand side has more energy, you need to add energy into it to thus have it being balanced. I can also show it to you with this graph. So you see in this graph, you see that what's going on is that when hydrogen and chlorine comes together, they need to give off energy to form HCl. While the opposite was true in this previous example where the hydrochloric acid needed to add energy to break it apart into hydrogen and chlorine. So this is the example of what I mean by forming and breaking bonds. We're now going to go into a different type of example, a different type of terminology we call enthalpy, which will then lead us into what we call exothermic and endothermic. And thus now we could use these ideas to help us calculate. So what is enthalpy? Enthalpy is defined as the heat contained in a system. So whatever heat is in that system, that thing you're studying, that is enthalpy. And the units of enthalpy is kilojoules per mole. So we have this unit of kilojoules per mole because kilojoules is energy. But this energy has to be somehow put as a unit rate with regards to moles, because something that's much larger that has more particles might have more energy. But how is that in terms of its unit rate? Now we can also represent it by a symbol. The symbol we use for enthalpy is capital H. You can think of it as heat. So when you discuss this, what occurs is that delta H is going to be, well, delta means change. It's the change in enthalpy. And if it's a change in enthalpy, well, then we could write this as an equation where delta H is equal to H of the products minus the H of the reactants. And the reason why this works is because usually in physics, for example, you could find change by finding the final of something minus the initial something. In chemistry, we call that final products. We call that initial the reactants. So this relates us to the next two things. Why do things feel hot? Why do things feel cold? And it's due to this idea of what we call exothermic and endothermic. So, exothermic. When something is exothermic, what that means is exo means to release. So exothermic equals exit. So if you think about it, the EX makes sense. It's exo, exit. And it means too, what that means is you are releasing heat to surroundings. So it releases heat from the system, whatever you're studying, to the surroundings, and thus, because of that, your surroundings gets hot. So if you think about it in terms of, for example, when you sometimes could mix, I don't know, anyone ever mix concrete or cement with water? That's what we call exothermic reaction. The concrete or cement mixture will get hot. So here's an example of this case where if you write a reaction, this is what's going on. You're gonna have CH4 plus two oxygen gas molecules will form, and thus will be a combustion reaction to form CO2 and H2O. But you're also gonna get a release of energy. And really, how much energy gets released from this reaction, which is methane? You're gonna form 891 kilojoules per mole. Now, you don't need to know where this energy number comes from. You just need to know, well, if you release energy, it's exothermic. Now, let's think about it for a second. If we release energy, are we breaking bonds or are we forming bonds? Well, if you go back to our previous example, when you see that you are releasing energy, that means we're forming bonds. So in this case, usually exothermic reactions are, in a sense, you are forming bonds. Okay. Now we call this notation, so this style of writing a chemical equation with energy, we call this a special name. We call this the thermal chemical equation, because not only is it a chemical equation, it's showing you the energy involved now. Now, if you need more room, you can flip the page over to the next page. What's delta H? Well, if the products have less energy than the reactants, delta H, remember, is the change in enthalpy. It's the enthalpy of the products minus the enthalpy of the reactants. Well, if the reactants have more energy than the products because you released energy, then delta H will what we call negative. But negative by how much? Well, it released 891 kilojoules per mole. In this case, because you released that much, that is how much you need the difference between your product and reactants. Thus, delta H is equal to negative 891 kilojoules per mole. So if you need a diagram of what exothermic looks like, this is the diagram showing you what's going on. Your system's releasing energy to the surroundings. Now, if we talk about this backwards, We're going to discuss this now in terms of endothermic. Endothermic. Endothermic, as you could see, as you could call it enter. So if I write this endothermic, must equals enter. So now energy enters into the system from its surroundings. So in this case, you're now absorbing energy from surroundings. When this occurs, though, what's going to happen? Well, you might think because it's absorbing energy, the object should get hot. The system will get hot, but it's actually not the case. What you're feeling is that you're feeling the surroundings. So when this occurs, the surroundings, whatever you're working around, will get cold. An example of this would be, for example, an ice pack. When you hold an ice pack, the reason why it feels cold is because your hand is the surroundings. And it's absorbing the energy from your hand into the ice pack, and thus your hand gets cold. So if you look at the thermochemical equation here, we see that here is KCl3, and we add energy into it to break the bonds. And when we add energy into to break the bonds, we add, in this case, 41.4 kilojoules per mole to do this. So what must delta H be this time? Well, delta H, again, is equal to the enthalpy of the products take away the enthalpy of the reactants. Well, this time, the reactants have less energy. That means this is less energy. We take away something that's smaller, it becomes positive. So delta H this time is positive. But positive by how much? In this case, it's going to be positive by the amount you added. So it's positive 41.4 kilojoules per mole. And here's a diagram showing you this is the case. The surroundings absorbs energy into the system. So when this occurs, the surroundings gets cold. Now, if I could spell surroundings, I'll work out. Surroundings gets cold. So in this case, the surroundings could be, for example, your hand, right? Your bottle, your ice pack. It could be anything that is the surrounding of the system. So it could be a hand, your cup, bottle, any of that could be a surrounding. All right. So now we're going to progress using these thermochemical equations, and now we're going to talk about it in terms of calculations. Now, there's usually a demo I would do with ice pack if this was in class, but I'm just demonstrating to you how ice packs work. If we have time in the future, we'll do a demo of the ice pack, but for now we don't. So is there another way to represent enthalpy? And there is. We could use what we call delta H notation. So not the thermochemical equation. Instead, we write it where we write our chemical equation and then we write our delta H afterwards. So in this case, what we do here is delta H notation is where we have the chemical equation, the typical equation we've always had, and then at the end, we put delta H is equal to something. So an example of that is if something is endothermic, for example. Like, for example, the one we just did, which was KClO3 plus 41.3, I think it was 41 or 41.4, yep, 41.4 kilojoules per mole. We don't write it there. We don't have to. Instead, we put our chemical equation as so. And then at the end, we write our delta H. Now, because it's endothermic, it's going to be positive delta H, 41.4 kilojoules per mole. And if it's exothermic, then it's going to be the opposite, where, for example, you have CH4 plus O2 will give you Cl2 plus H2O. So that's the example we did earlier. You would see that in this case, if I balance this equation out, you see that this one, the delta H was 891, but it's negative 891 kilojoules per mole. Correct? I think so. Let's check it out. 891, yep. So this is what we call delta H notation. It's where you have your chemical equation, and then with a little semicolon, delta H is equal to whatever value. So how does mole and heat relate? What does all this have to do with anything we studied? Well, we know how to calculate different things with moles. But now, because, look at this, our delta H notation, if I add to make sure this is delta H, our delta H notation now has a conversion factor. This is kilojoules per mole. That's a conversion factor. So we have a new conversion factor. Now, this is where it gets a bit tricky. So if you need to pause this video at any time, please do so and rewind and rewatch, okay? So if you look at this previous example, the one with methane, this one, how this works is this is per whatever mole you have. So what does that mean? Well, if we know it's negative 891 kilojoules per mole, we need to know how many of the mole we have. Now, where do we find that number? How many? Some number of x. That x comes from the coefficient we have in front of our balanced equation. So if we're talking about it, for example, about methane, then this would be negative 891 kilojoules per 1 mole. But if you're talking about for oxygen gas, this one, on the other hand, will be negative 891 kilojoules per 2 moles, because the coefficient in front of the oxygen gas is a 2. So we gotta make sure that is the case when we're dealing with this situation. So let's practice this using this conversion factor in the equation. Now you can cross out this example here, alright, because it doesn't really pertain to us that much. Where I'll go into is how to use this in the equation, and then we're going to start moving on to example. Okay, so again, if we're talking about it with this example, let's use it for another example. Let's talk about it in terms of, let's say, I don't know, let's create an example of another type of combustion. Okay, plus let's say, for example, it does, I don't know, 1,000 kilojoules per mole. Okay, let's say this is a reaction for ethane combustion. So if we balance out this reaction, we're going to see that we need to do our double odd even rule, because all of a sudden we have an even number of oxygen but odd number of oxygen on this side. So we double all these numbers. This becomes a 4, this becomes a 6, and this becomes a 2. Now we balance our oxygen because we have 8 plus 6. 8 plus 6 is 14, so we need 7 oxygens here. So in this example here, our conversion factor, let's talk about, for example, C2H6. It will be now, what you're talking about here is, for this conversion factor, it's going to be 1,000 kilojoules over 2 moles of C2H6, negative 1,000 kilojoules. If we're talking about in terms of oxygen gas, it's going to be negative 1,000 kilojoules per 7 moles of oxygen. And if we're talking about for carbon dioxide, it's negative 1,000 per 4 moles of carbon dioxide. And if we're talking about for water, it will be negative 1,000 kilojoules over 6 moles. So this one is for CO2, and this one's for water. So this is how we can now use these as our conversion factors. Let's see what we get. So let's practice this with this example right here. The one we just talked about, which is the combustion of methane. So this is our first question. It says that how much heat is released during the formation of 12.5 moles of CO2. So we want to talk about CO2. It's 12.5 moles. So we have our 12.5 moles of CO2. And we want to multiply this moles and get us to heat, which is energy. So we have this conversion factor right here to help us convert. Now, what is the coefficient in front of the CO2? It's a 1. So that means this mole right here is a 1. So we write it as 891 kilojoules per 1 mole. As you see now, your moles cancels out. And you're left with just kilojoules. And when you plug this into your calculator, you would see that you have 12.5 times 891. And you're going to get 11,137.5. So 11,137.5 kilojoules. But this needs sig figs. So you write this either as, if you're talking about, because there's only 3 sig figs here, we could write this either as just 11,100 kilojoules, or in scientific notation, 1.11 times 10 to the 4 kilojoules. Either or will work. Now, if you want to pause the video to try the next one, you can. But if not, I'm going to progress on to the next one. So this one you have 26.79 grams in. 26.79 grams of CO2. So our first step is we need to get to moles. How do you get from grams to moles? You use the molar mass of CO2. So what is the molar mass of CO2? Well, if you look at your data booklet, you're going to see that carbon is 12 and oxygen is 16, but CO2, which is you have 2 oxygens, so 16 times 2 is 32 plus 12, that is 44.0 grams per mole. So we have that as our conversion. So we want to cancel our grams, that means our moles goes on top and our 44.0 gram goes on the bottom, and thus our grams will cancel out. And now we're in moles, we can now use the energy term. So as you see here, CO2 again is, in this case, 1 mole. So if I multiply this by 891 kilojoules per 1 mole of CO2, we're going to see now again our moles cancels out. And we're left with just kilojoules. That's the unit we want to solve. So what you see here is we have 26.79 divided by 44 times 891. And we're going to get 542.5 because it's 4 sig figs. So 542.5 grams. Or 542.5 kilojoules. Now what if this CO2 was for example, an H2O? What if it was talking about water? Then that means this number right here would be a 2 instead. And if you're talking about, if it was 3 moles, for example, then that would be a 3. So this is how we use our heat term as a way to calculate with moles now. Now your homework is page 120, and it states here that it's number 68 to 80 evens. So I want you to try out this homework and in your Hebden and see if you could use these to help you calculate. Like always, make sure you stay safe and healthy, and I'll see you next time.